Hi, everyone. We're going to kind of skip around a little bit compared to your book, and we're going to talk about complement. Complement bridges the first and second line of defense, as well as adaptive immunity. Okay, so here we are. This is the classical pathway of the complement cascade. And you can see that there are a lot of different numbers here. These numbers were designated numerically according to when they were discovered. The activity eventually results in lysis of the foreign cell. Okay, the cell breaks down, it kills. It also indirectly triggers inflammation and fever. It can be activated three ways. This is a classical pathway. Then there's the alternative pathway, and then there's the lectin pathway. Okay, so you can see here, this is a protein, C1 protein. It becomes an active enzyme when it binds to an antibody-antigen complex. Antigen-antibody complexes, that's from the adaptive immune system, okay? And so here you have the antigen, the antibody, and the enzymatic C1. We're going to go through all of these steps in a video, and then eventually you'll have the membrane attack complex that will cause an opening in the cell wall of the bacteria, allowing water to come in and allowing the cell to lyse. So let's look at the overview of the complement system.
The complement system is a set of proteins that circulate in the blood serum. When activated, these proteins work together to destroy foreign cells by cytolysis, to activate the inflammatory response, and to assist in phagocytosis. The main components of the complement system are called C1 through C9.
Okay, so the classical pathway, you have a foreign substance, which is an antigen, the antibody that's produced by the adaptive system, and then complement proteins 1, 2, and 4. The alternative pathway, the microbe has C3 on its, something on its surface that allows C3 to attach. And then the lectin pathway has mannose on the surface where lectins attach. So let's look at activation video.
Complement can be activated through three different pathways: the classical pathway, the alternative pathway, and the lectin pathway. The classical pathway was the first activation pathway of the complement system to be discovered. The classical pathway begins when a pair of antibodies attach to antigens, such as proteins or a large polysaccharide on the surface of a bacterium. The antibodies bind and activate C1. C1 then cleaves several copies of C2 and C4. Together, the C2A and C4B fragments form an enzyme that cleaves C3, activating the complement system. The alternative pathway of complement activation was so named because it was discovered after the classical pathway. While the classical pathway requires antibodies specific to the invading microorganism, the alternative pathway requires three complement proteins called factor B, factor D, and factor P, or properdin. These proteins are attracted to microbial cell surface material, such as the lipid carbohydrate complexes of certain bacteria and fungi. Together with C3, these proteins result in the cleavage and activation of C3 proteins, which in turn activate the rest of the complement system. The most recently discovered pathway of complement activation is the lectin pathway. When macrophages ingest material through phagocytosis, they release chemicals that stimulate the production of carbohydrate binding proteins called lectins. The lectins bind to distinctive patterns of carbohydrates on the surfaces of certain bacteria and viruses. The lectins themselves can act as opsonins for phagocytosis, but also activate C2 and C4, which leads to the activation of C3, leading to the activation
of the rest of the pathways. So here you see, we've got everything here where you have the C5A and C5B. All right, and then C5B combines with C6, C7, and C8. We saw that in the video, but also with several molecules of C9. And that forms the membrane attack complex, which drills the hole into the pathogen cytoplasmic membrane, leading to lysis of the cell. And this is a photomicrograph of the membrane attack complex. You'll see it's a transmission electron micrograph. And this is the scale of 40 nanometers. Okay, so the results then in a video.
Once the complement cascade is activated, several events occur that ultimately result in the destruction of the pathogen. C3A and C5A act as chemotactic factors, attracting phagocytes to the site of infection. C3A and C5A also bind to mast cells, triggering the release of histamine and other chemicals as part of inflammation. C3B acts as an opsonin, coating the invading cell. This coat makes it easier for the phagocyte to adhere to the invading cell during phagocytosis. C5b binds to C6 and C7, which attach to the plasma membrane of the invading cell. C8 and several C9 molecules bind to the C5b, C6, C7 complex, forming a cylinder-shaped membrane attack complex, or MAC. The MACs form circular holes in the membrane of the invading pathogen, causing water to enter the cell and ions to leave. This results in cytolysis, killing the cell.
Okay, so this complement system is really important to the first line, the second line, and also to adaptive immunity. Let me see if I can go here. All right, so if you go to microbiology diseases and you look at the study area, study by chapter, and you get to chapter 15, you will see that there's a lot of videos in a line here. The complement system, then inflammation, and then phagocytosis. You can go back and look at these over and over again, and I recommend that you do that when you're studying. The complement system will make more sense after we look at the second line of defense again, and then you can't, or not again, after we look at the second line of defense, and then you can look at complement again. Complement is going to also be useful in the adaptive immune system. So complement is something that you should really study, and you should be familiar with all of the different steps in it. And next we'll have the longest of these, looking at the secondary line of defense.